This is the review that we did from class. I'm going to post it to YouTube so that you guys can use it to study for tomorrow's test. Okay, our first question asks, which of these is the correct electron configuration for potassium? So there's a couple of ways that you can go about solving this, and there's a couple of shortcuts that you can use as well. Okay, for one thing, we need to find potassium on the periodic table, and it happens to be right here, and it's number 19. So one trick you can use is you can first check and see, do all of these or any of these add up to 19? If only one choice adds up to 19, then that's going to be your answer. Potassium has 19 electrons. It has to be the one that adds to 19. In this particular case, though, you'll see that all of these add up to 19. So we need to use something else to solve this problem. Now, the long way of doing this is we can go back and we can say, okay, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, etc. And we can literally write out the electron configuration and say, okay, so this is going to be 1s2, and then 2s2, and then it's going to be 2p6, and 3s2, and 3p6, and then we're going to get to 4s1, and that's going to add up to 19, in which case that tells us that our answer is B. But if you remember what I told you guys about the periodic table, you don't even have to go through all of that work in order to do this. All you really need to do, if I scratch this out, is remember the setup of the periodic table. So the periodic table is set up so that everything in the first column is going to end with S1. And this is S2, and then this is going to be P1 all the way to P6, except for helium here. Everything here is going to end with D1 to D10, and everything here is going to end with F1 to F14. So technically, if we just follow that rule, if we go n equals 1, n equals 2, n equals 3, n equals 4, this ends with 4s1. So since this ends with 4s1, only one choice here ends with 4s1. The rest of these end with other things, and so we would know automatically that this would have to be potassium. While we're on this slide, really quick, let me make a quick comment about writing abbreviated electron configurations. So one of the other things you have to be able to do is write a shorthand of this. So reminder, all we really care about for all of these electron configurations is going to be our valence electrons, meaning the ones that are on the very outside. So if I erase all this, and we go back for a second, and we look, you see that this ends with 4s1. Our highest level is level 4, and it is one electron, or there is one electron in level 4. Therefore, we only have one valence electron. If we were going to draw the dot diagram for this, it would look like this, potassium with one dot. All the other electrons are in a level lower than 4. 1s2, 2s2, 2p6, 3s2, 3. These are on level 1, level 2, level 3. So what we can do is find the closest noble gas to potassium that's smaller than potassium. So if we go back, that's going to be neon. It's the closest noble gas. Remember, these are our noble gases here. It's smaller than potassium, and it's a noble gas, and that would represent basically this noble gas stable inner core. So neon with 4s1 would be our shorthand way of writing the same electron configuration. It basically means that all the electrons under the outer shell look just like neon, and then after that point, there's one electron in the outer shell. And we can also draw what we call an electron dot diagram showing that potassium has only one electron in the outer shell. When we do electron dot diagrams, we basically just draw the valence electrons. Since the valence or outermost electrons in this case would just be one electron, we would draw potassium like this with one dot. You could also draw the dot over here, or you could draw the dot down here, but the bottom line is you would draw one dot, and that would be the electron or Lewis dot structure showing just how many valence electrons it has. Okay, next question. Principal quantum number is represented by which letter? And that answer would simply be N. n is our quantum level, n equals 1, n equals 2. The next thing after that are going to be our sublevels, and so on sublevel n equals 1, there is an s sublevel. On n equals 2, there's two sublevels, 2s and 2p. On n equals 3, there's 3s, 3p, 3d, and on 4, there's 4s, 4p, 4d, 4f. So these are sublevels. S, P, D, and F are our sublevels. N represents our, sort of like our floor. The rule that says that electrons occupy the lowest energy level first is the Aufbau principle. You don't have to know the names of these for our test, but you do need to be able to follow the rules. So the Aufbau principle is basically the one that explains why you follow the arrows. Because despite the fact that, for example, 3D is on the third floor, we don't actually fill the whole third floor before we go to the fourth floor. We fill them in order of energy, and it turns out it takes less energy to fill 4S than it takes to fill 3D. So it fills in this order. Our second rule, the Pauli exclusion principle, is the one that says that only 2 electrons can occupy a particular orbital. So for example, S has 1 orbital. The sublevel P is like a 3-bedroom apartment. It has 3 orbitals because P itself is a dumbbell shape. So this would be a P on the x-axis, but there can also be a dumbbell shape drawn on the y-axis, and we can even draw a dumbbell on the z-axis. So because there's 3 different orientations or ways we can draw the dumbbell shape, there's actually 3 different areas where electrons can be found. So the Pauli exclusion principle would say, again, that electrons, you could only have 2 per bedroom. Even though P, the 3-bedroom apartment, holds 6 electrons, you can only have 2 per bedroom. That's why D, which was a 5-bedroom apartment, can hold exactly 10, because again, 2 in each bedroom. And F is a 7-bedroom. It has 7 different orientations where you can find electrons. And that means it could hold exactly 14 electrons. So this is our very sloppy orbital diagram. And the last one is Hund's rule. Hund's rule says that when electrons are in the same apartment, for example, let's say you are filling a P apartment, you would not, let's say there's exactly 3 electrons in 2P. So if there are 3 electrons in P, you would do this, 1, 2, 3. You would not see them like this, 1, 2, 3, because they don't want to be next to each other. That's Hund's rule. And then Heisenberg's uncertainty principle is the one that says that you can't know, I believe it's the position and the speed of an electron at the same time. So we only have orbitals, areas where we feel there's the highest probability of finding an electron, not exact orbits where we know exactly where an electron is and what direction it's going or any of that. You can't measure that directly. Alright, this one asks what the shape of P is. So again, S is an orbital that has a sphere shape. Since there's only one way you can draw a sphere, whenever there's an S, it's a 1 orbital apartment. P was a dumbbell shape, which is the answer to this question. And because there's 3 different ways you can draw that in space, that means there's 3 different P shapes. And so P is actually a 3-bedroom apartment. There's actually 3 orbitals, 3p orbitals that exist. The clover is actually D. It's actually considered a clover shape if you were to look it up, but bottom line is there's 5 ways you can draw it. So there's 5 d orbitals, and then F had 7. And they always just say it's complex. Honestly, I've only ever really seen people ask about the shape of S and P. Beyond that, it gets complex. How many electrons can be held on level n equals 4? Well, there's an easy way to solve this. There's a formula, 2n squared. So on level n equals 4, 4 times 4 would be 16 times 2. There would be 32 electrons that could be placed on level n equals 4. Remember, on level 1, there was only a 1s, and that means 2 times 1 squared gave us 2 electrons. On level 2, there was 2s and 2p. 2 times 2 squared is 8, which makes sense. S could hold 2, and p could hold 6, and that adds up to 8. On level 3, we had s, p, and d. Again, this can hold 2, this can hold 6, and d could hold 10. That adds up to 18, but you can also work it out. 3 squared is 9, times 2 is 18. We just did level 4, that's 32, and we could keep going. Level 5, level 6, etc. And that's the maximum number of electrons they can hold. Whether they ever actually end up holding that many is a different story. Okay, so before we move on, just a quick reminder of the different things that you can be asked to do with an element on the test. So let's say that we were going to do strontium, SR. So this is number 38. So for strontium, you could be asked to write the electron configuration. You could be asked to write the abbreviated electron configuration. You could be asked to write the electron dot structure for it. And you could be asked also to draw the orbital diagram for it, which is the one with the arrows, which I'm not going to do right now. So, for the electron configuration, the easiest way to do this would be to just figure out what it's going to end with, and then you can just write everything up to that point. So, remember, this is column 1, and this is column 2. Everything here ends in S2. Also, we can count down 1s, 2s, 3s, 4s, 5s2. So I already know that strontium's going to end with 5s2. So I can kind of cheat like that, and I can write out the electron configuration then up to 5s2 following the arrows. So I already know this, but 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Again, you could use your arrows to write this out. So that's a lot of work. That's our electron configuration. Since we really only care about valence electrons, our top floor, we can look at everything prior to that point, before we get to that top floor, as our inner core. And our inner core is always going to represent a noble gas, because noble gases all are completely stable and they have their floors filled. So the closest noble gas to strontium is going to be krypton. So krypton has the electron configuration basically up to 4p6. And then 5s2 is all you would have to write, showing that these are our 2 valence electrons after the inner core. Now, electron dot structures are basically a diagram showing just the dots. So for strontium, since it has exactly 2 electrons, we just showed, in its outer shell, it has 2 valence electrons, we would draw 2 dots. You could draw it like this, you could draw it like this. As long as you don't put them next to each other, this would be wrong, because we're sort of representing how they don't like to be next to each other, and how those are unpaired electrons that could be involved later in bonding. All right. Couple of really quick shortcuts on this, just for any time that you're asked to draw an electron dot structure. At least in this chapter, we're keeping it very simple. So in this chapter, since everything here ends in S1, everything in our first column is going to have 1 valence electron. And these end in S2, so they all are going to have 2. This is D. They do some weird things. Technically, if we think about it, since 4s fills before 3d, then anything that ends with 3d something probably has 2 valence electrons. But moving on, everything in the third column is going to have 3, because it's going to end with S2, P1. Everything here is going to end with S2, P2, so 4, and we just keep going, 6, 7, 8. And so this is how many valence electrons we would find in things in each column. So everything in this column, except for helium at the very top, has 8 valence electrons. Everything in this column, for example, is going to have 4 valence electrons, and so on. And one last thing that you can do with this is you could actually, rather than doing the valence electrons, you could be asked to say what kind of ion it's going to form. So when we talk about ions, we're talking about what is it going to do to get a stable outer shell. All of these on the end, they have stable outer shells. The whole reason why they don't react with anything for the most part, they're noble gases, is because they all have 8 electrons in their outer shell. They basically have S2P6. Their highest floor is completely filled, except for helium, which just ends with S2, but remember, helium's on the first floor, there is no P. So 1s2 is a full outer shell. All right, so if we look at valence electrons, we just said everything here has 1. Now, that means that, for example, if we were to look at potassium, potassium had argon and then 4s1. Well, the question is it going to be easier for it to gain another 7 to look like krypton, or is it going to be easier just to lose that 1 and then it'll look like argon? So it's going to be much easier to lose 1 electron. If it loses that electron, potassium will now have the electron configuration of a noble gas. So all the things in the first column all form a +1 charge, because for all of them, since they all have 1 electron in their outer shell, it's going to be much easier for them to lose 1 electron than to gain 7. So these all form a +1. Second column, similar. We just showed strontium had 2 electrons in its outer shell. It ended with krypton and then 5s2. For strontium, it's going to be much easier to lose these 2 and look like krypton than it would be to gain another 6 and look like our next noble gas, xenon. And this is going to be true for everything in the second column. So everything in the second column is going to form a +2 charge. And that doesn't mean add 2 electrons. It means it's going to lose 2 and end up with a positive charge, because remember, electrons themselves are negative. So losing electrons is going to give it a positive charge. Skipping over these, which lose different numbers of electrons, we're going to skip that, make a beautiful patriotic diagram there. So now we get to these over here, which all ended with, basically they all ended with S2 and then P1. They have 3 electrons in their outer shell. It's still going to be easier to lose 3 electrons than it would be to gain 5 and look like the next noble gas. When we get to the next one, we see 4 electrons in the outer shell. Now this is kind of unique because you would either have to gain 4 or lose 4, and that's sort of a tie. So what's going to tend to happen here is a lot of these, like carbon and silicon, are actually going to end up sharing. They're not going to form a charge at all. When we get down here to 10, it does tend to sometimes form a +4, and lead can also form a +4. But if we think about these up here, they do tend to share. They form covalent bonds instead. Now we're going to see the opposite situation arise. These all have 5 in their outer shell. There's a 5 there. It's going to be easier to gain 3 and look like the next noble gas than to get rid of 5. The shortest way to 8 is going to be to gain 3. That means these are going to tend to form a -3 charge, meaning gaining 3 more electrons, -3 charge. Column 6 here have 6. If they gain 2, they'll have 8. Column 7, if they gain 1, they'll have 8. And then again, our noble gases, for the most part, we're going to assume are unreactive and are not going to form charges at all. So that gives you a little, I guess, heads up on the ions and on the dots. All right, this question asks what element this is. So again, there's multiple ways you can solve this. One way you can solve this is by simply adding up the electrons. So if you look at this and you literally add up all these are our electrons, and you add all of these up, you're going to find that there's 32. You go to the periodic table and find number 32, and that's germanium. Also, if you remember how to use the shortcut and know how the periodic table is set up, I could also say, okay, I know this is level 1, this is level 2, this is 2s, and this is 2p, this is 3s, this is 3p, 4s, then 3d, then 4p, and this is p2, p1, etc. I can basically look at this and I know that germanium is going to have to end with 4p2. So assuming this is something at ground state, which we haven't talked about in this chapter things, the electron configurations for ions, this would be end with 4p2. And just for practice purposes, let's say that we had to write the abbreviated electron configuration for germanium. Well, we would find the closest noble gas that's smaller than germanium, and that would be argon. We put that in brackets, and that represents all the electrons in the inner core. If we go back up to the longer abbreviation, that would basically give us everything up to here. Because once we filled that, we then go back and we would fill these. So 4s2, 3d10, 4p2. And even though we wrote 3d10 here, if I asked you how many valence electrons this actually has, technically you only count whatever's the top floor. So it would be our 4s2 plus our 4p2, so there would be exactly 4 electrons, 4 valence electrons on the outside, which means if I asked you to draw the dots for germanium, which represent the valence electrons, you would draw it like this. 1, 2, 3, 4. They don't want to be next to each other, so it would be incorrect to do, say, this or something akin to that. You would put 1 on each side. All right, next question, which level below has the lowest energy? All they're really asking you here is they're asking you to remember our levels of, our order of filling. So it was 1s, then 2s, and 2p. This is the order of lowest energy when we follow the arrows. So 4p, 4d, 4f, 5s. I'm just going to go all the way up to 5f since that's a choice. And then we could put them all in order. So, all right. So if we do our arrows here, 1s first, then 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and we would keep going. So that means if we're putting these in order of lowest energy, the first one here that would have the lowest energy would actually be level 4s. After 4s, it would go back and fill 3D. Then if that got filled, it would then go to 4P, then 5S, and you notice that we don't get to 5P or 5F until much later on. After 5S, we're going to go back to 4D, then 5P, and then 6S, and 5F does not get filled until much, much later. Okay, which of these is the correct orbital diagram for oxygen? So oxygen is right there. It has 8 electrons in its outer shell. So we're looking for, first of all, one that has 8. Well, again, if you add them all up, that shortcut's not going to help because they all have 8. But we also know that they're going to fill in order of lowest energy first, and they're not going to go to the next level until the level before is full. So 1s would fill first, then 2s, then 2p, and then if need be, we would go to 3s, and then we would go to 3p. So this one, D, is wrong because we're only putting 1 electron in each, and we would fill 1 orbital before we go to the next, or 1 level. And this one starts off okay. This one's full, and then these 3, but you wouldn't go to 3s. You'd have to fill P completely before you'd ever go up to level 3. B is incorrect because in B, we broke that rule. They don't want to be next to each other. So before you'd find 2 electrons sharing an orbital, you would have put at least 1 electron in this one. And that's why A is your answer. It would fill 1s2, then 2s2, and then since there's 4 in P, the first 3 would go in and be separate from each other. 1, 2, 3. And then the 4th one would come back and share. All right, how many sublevels are found on level n equals 3? So the sublevels, remember, were sort of like the apartments on that floor. So on level n equals 1, we had only 1 apartment, the 1s. On level 2, we have 2s and 2p. On level 3, we have 3s, 3p, and 3d. So our answer is there are 3 sublevels on n equals 3. That's not how many orbitals there are, because remember, S has 1 orbital, P actually has 3, and D has 5. So the number of orbitals on the 3rd floor would be 9. And the number of electrons that could be held, since each of those can hold 2, would be 18. Okay, which of these is not true about electrons? First, electrons have fixed amounts of energy. Technically, we could say that's true because they live on a particular level, on an energy level, with a particular amount of energy. So we know that if it's living in, for example, 2p, we know that electron has a particular amount of energy. We also know, this is true, that the measurement of energy is done using quanta, a quantum, which is the same thing from our previous chapter, or the previous part of this chapter, with energy is equal to frequency times Planck's constant. A quantum is Planck's constant. So the amount of energy in electrons has to do with jumping from level to level. It has to do with quanta. It just can't go anywhere. I told you it was more like stair steps. They're found on discrete levels. D is false. They are not moving in orbits. Orbits means it's a predictable path. They are in orbitals, which is sort of like a probability. And C is also wrong. They're not evenly spaced. As we go away from the nucleus, the spacing actually changes. They get, I can't remember if it's farther apart or closer together. I hate to say that. But it's not even. You can check the notes and you can let me know tomorrow. Okay, this is an easy one. The lowest, most stable state of an electron is called the ground state. When it gains energy and jumps up, that's called its excited state. And then when it comes back down, let's say that it was living on n equals 1, it gets excited, it jumps all the way up to level n equals 5, or this would actually be 4. Then when it comes back down, that's when it's going to release the energy, and that was the whole idea of the bands of light that we saw, when the electron comes back down to ground state from its excited state. Okay, Heisenberg's uncertainty principle was just the rule that said we cannot determine its speed and position at the same time. Charge doesn't change with speed. Position doesn't determine speed. They are constantly in motion. That's a true statement, but that's not what Heisenberg's uncertainty principle says. And they do move in an unmeasurable path. It's an orbital, which is an area where they're moving, but we can't detect it. But again, that's not what the principle says. The principle says you can't measure the speed and position at the same time. All right, and our last question, what kind of charge will oxygen gain when it forms an ion? So this question actually goes along with what I showed you about the periodic table and forming ions. So I'm going to stretch this out a little bit. So oxygen is located over here. This is oxygen. Right here. All right. If we write out the entire thing, you're going to see that it's going to be 1s2, 2s2, 2p4. That means that you could add up the outermost electrons. Technically, its short abbreviation would be helium. And then 2s2, 2p4. So it has exactly 6 electrons in its outer shell. If you recall, I also told you everything here has 1, 2, 3, 4, 5, 6, 7, and 8, except helium, which has 2. All right. So what kind of an ion will it form? Well, remember again, what I told you about that is if it's in the first column, it's going to lose 1. These are going to tend to lose 2. These are going to tend to lose 3. These are going to tend to share, except for a couple down here. These are going to tend to gain 3, -3 charge for 3 extra electrons, gain 2, gain 1, and these are going to tend to not form ions. So oxygen is in column 6. The easiest way to get to 8 is that it's going to gain 2 electrons. That means it's going to tend to form D, a -2 charge. So it would be O, -2. What would sodium do? Sodium is in our first column. Sodium would tend to lose 1 and get a +1. If it did that, it would now look like the noble gas right before it, which is neon. If oxygen gained 2, by the way, it would also look like neon. Oxygen would now have, with its extra 2 electrons, the same electron configuration as neon. All right, so that was it. That was the review that we did in class. The things you really must know, for one, you definitely need to be able to draw in the arrows and know the order that things fill. So you need to be able to, if I'm just drawing this out, 4s, 4dp, sorry, 4d, and then it would be 4f, and then we would keep going. And then you have to remember it's going to fill in this order: 1s, then 2s, 3p, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and it would keep going. If you can't do that, then what's going to happen is if you get an element that's one of the larger ones and you're asked to write the configuration, you're going to write it wrong. The other thing that you're going to have to remember always is that s can hold 2, p can hold 6, D can hold 10, and F can hold 14. That's really important too, because I've seen people write, 1s2, and then 2s2, and then 2p2, and then 3s2, and because they didn't fill up P before they moved on, they're going to end up with the wrong configuration. So it's really important you know the maximum number of electrons something can hold. You also need to make sure that you know how to write the abbreviated electron configurations. Remember, find the closest smaller noble gas. The easiest thing, the thing that will really save you on this, is memorizing the order on the table. That this is S block, that this is D, that this is P, and that down here is F. That's going to help a lot because you're going to be able to look at the table and know immediately, oh, it's located here. It must end in 3D2. Etc. There are a couple exceptions. If you want to keep watching, I'll show you those on the next slide. I don't think I have any questions about it on the test, but it could be bonus. All right, exceptions to the rules, if you're interested. Here's the thing. It is more stable when we're filling D particularly. It tends to be more stable for D to be either half full or completely full if it's possible to do that. So, for example, things in this column should end with S2. For example, chromium should end with 4s2, 3d4. What we've discovered is because of this rule that D tends to want to be half full, it will actually steal one from S, and we'll actually end up with the real electron configuration of 4s1, 3d5. So this is an exception to the rule where one gets sort of promoted to D and it makes both of these half full, which is more stable than this one being full and this one being partial. And we're going to see the same thing happen over here with copper. Copper should end with 4s2, 3d9, but I guess because D is really big and it sort of has some pull there, what it's really going to do is it's going to steal one from S, and this is going to end with 4s1, 3d10. That's going to make D full, and S half full, and half and full are both kind of more stable than what you would get the other way around. So those are exceptions. For our class, we're not talking about, oh, well, does silver do that? Does the gold do that? The answer to that would be that it's very likely. But we're not memorizing which ones do and which ones don't. So you could make an educated guess that probably anything in this column might do a similar thing to chromium, and anything in this column might do a similar thing to copper.